Rotational motion is a fundamental concept in physics, describing the circular movement of objects around a fixed axis. The principles of moments explain how forces acting on an object can cause it to rotate or remain in equilibrium. These principles have important practical applications in areas like engineering, architecture, and everyday life. Understanding moments is key to analyzing and predicting the behavior of rotating systems, from simple levers to complex machinery. By mastering the principles of moments, we can design more efficient and effective solutions to a wide range of real-world problems. The concept of moments is fundamental in understanding the behavior of physical systems. Moments refer to the turning effect produced by a force acting on an object around a specific point or axis. We can visualize moments using the analogy of a lever, where small force applied at a long distance can produce a larger effect than a larger force at a shorter distance. Moments play a crucial role in maintaining rotational equilibrium, where the sum of all moments acting on an object is equal to zero. Understanding moments is essential for analyzing and designing systems that involve rotational motion or forces. A moment is a measure of the tendency of a force to cause rotational motion around a specific point or axis. It is calculated by multiplying the magnitude of the force by the distance from the point of application to the axis of rotation. Moments are crucial for understanding how physical systems and objects behave when subjected to external forces. The diagram on the slide illustrates the concept of a moment, showing the force vector and the distance to the axis of rotation. Moments play a key role in many areas of physics and mechanics, such as in the analysis of structures, machines, and the motion of rigid bodies. The key components of moment of a force are magnitude, distance, and angle. Magnitude refers to the strength or intensity of the force. Distance is the perpendicular distance from the axis of rotation to the point where the force is applied. Angle is the angle between the force and the line connecting the axis to the point of application. The moment of a force is the product of these three factors: magnitude, distance, and the sign of the angle. This moment causes the object to rotate around the axis. Understanding the relationship between these three elements is crucial for analyzing rotational motion and equilibrium. Moments are an important concept that allow us to apply forces more efficiently, giving us mechanical advantage to lift or move heavy loads with less effort. Understanding moments is crucial in structural engineering to analyze forces, ensure stability, and design safe, sturdy buildings and infrastructure. Moments play a key role in maintaining equilibrium, whether for a person balancing on a fulcrum or a mechanical system in stasis. These three key applications of moments, mechanical advantage, structural analysis, and equilibrium, highlight their importance across a wide range of fields and everyday situations. The key steps in calculating moments are identifying the forces, selecting a pivot point, and applying the moment formula. First, we need to determine the location and magnitude of all the forces acting on the object or system. This gives us the necessary information to calculate the moments. Next, we choose a point around which to calculate the moments. This is typically the point where equilibrium is desired. Finally, we apply the moment formula. Moment equals force x perpendicular distance from pivot to line of action of force. This allows us to quantify the moments acting on the system. Understanding and applying these three steps is crucial for correctly calculating moments in engineering and physics problems. The conditions for equilibrium are crucial for understanding how objects maintain a stable position. First, the sum of all forces acting on the object must be zero. This means the forces are balanced and in equilibrium. Second, the sum of all moments or torques acting on the object must also be zero. This ensures the object is not rotating or spinning. The forces must be equal in magnitude and opposite in direction to be considered balanced. Finally, the object must be in a stable equilibrium, where any small displacement will cause a restoring force to return it to its original position. Understanding these four key conditions is essential for analyzing the equilibrium of physical systems. The image on this slide illustrates the concept of balance and equilibrium using a seesaw. Moments are the key to maintaining this balance. When two opposing forces are applied, the net moment must be zero for the object to remain in equilibrium. This balancing act is essential in many areas, from mechanics and engineering to our daily lives. The interplay of moments is the foundation of many physical phenomena, from seesaw balancing to maintaining stability in structures. Understanding how moments work is crucial for maintaining balance and equilibrium in a wide range of contexts. Clockwise moment is a turning force that causes an object to rotate clockwise around a pivot point. Counterclockwise moment is a turning force that causes an object to rotate counterclockwise around a pivot point. When the clockwise and counterclockwise moments are equal, the object is in rotational equilibrium and will not rotate. The seesaw image illustrates these concepts visually, showing the balance of moments around the fulcrum. Understanding clockwise and counterclockwise moments is key to analyzing the rotational dynamics of objects. Moment of inertia is a measure of an object's resistance to changes in its rotational motion. It depends on the mass of the object and how that mass is distributed around the axis of rotation. The more mass that is distributed further from the axis, the greater the moment of inertia. Moment of inertia is a crucial concept in understanding the dynamics of rotating systems. It is widely used in fields like mechanics, physics, and engineering to analyze the stability and control of rotating systems like wheels, gears, and flywheels. Understanding moment of inertia is key to designing and analyzing the behavior of these types of rotating systems. The parallel axis theorem is a fundamental concept in mechanics that allows us to calculate the moment of inertia of an object about any axis. It states that the moment of inertia about any axis is equal to the moment of inertia about a parallel axis through the object's center of mass, plus the product of the object's mass and the square of the distance between the two axes. This theorem is very useful because it allows us to determine the rotational dynamics of objects, which is crucial in fields like engineering and physics. By understanding the parallel axis theorem, we can more easily calculate the moment of inertia of complex objects, which is an important parameter in analyzing their rotational motion and dynamics. The applications of this theorem are wide-ranging, from analyzing the stability of rotating machinery to understanding the motion of celestial bodies. The perpendicular axis theorem is a fundamental principle in mechanics that relates the moments of inertia about three mutually perpendicular axes. It states that the moment of inertia about any perpendicular axis is the sum of the moments of inertia about the other two perpendicular axes. This is a very useful relationship that allows us to calculate moments of inertia for complex shapes and systems by breaking them down into simpler components. The theorem is built on the concepts of moment of inertia and the parallel axis theorem, which we covered in the previous slides. Understanding and applying the perpendicular axis theorem is crucial for analyzing the rotational dynamics of rigid bodies. I'll walk through a few examples to illustrate how this theorem can be used to simplify moment of inertia calculations. The center of gravity, or CG, is the average location of an object's weight, the point where the entire weight can be considered concentrated. Knowing the location of the CG is crucial for determining an object's stability and balance. It's a key factor in mechanics of standing, sitting, and moving. Calculating the CG can be complex, especially for intricate objects. It requires considering the mass and position of each component. Advanced mathematical models may be needed to precisely determine the CG of complex shapes and structures. The CG is a fundamental concept in physics and engineering that has wide-ranging applications. The distribution of mass within an object determines its center of gravity, which is crucial for maintaining stability. When the center of gravity is aligned with the base of support, an object is in a stable equilibrium. Moments play a key role in this balancing act. If the center of gravity is outside the base of support, the object becomes unstable and can tip over. Moments determine the tipping point. Placing weights or applying forces to create counteracting moments can help stabilize an object and prevent it from tipping over. Levers are simple machines that use a fulcrum to amplify input force and generate a moment, or rotational force, around that fulcrum. The moment generated by a lever is equal to the force applied multiplied by the distance from the fulcrum to the point of force application. There are three main classes of levers, differentiated by the position of the fulcrum, effort, and load. Each class has unique mechanical advantages. Let's take a closer look at these three lever classes and their key characteristics. A first-class lever has the fulcrum position between the input force and the output load, allowing for a mechanical advantage. This is commonly seen in seesaw mechanisms. In a second-class lever, the load is positioned between the fulcrum and the input force, providing a mechanical advantage. This design is often used in wheelbarrows and nutcrackers. A third-class lever has the input force positioned between the fulcrum and the load, resulting in an increased speed of the output, but reduced mechanical advantage. This can be seen in tweezers and fishing rods. The key difference between these three types of levers is the positioning of the fulcrum, input force, and load, which determines the mechanical advantage and speed of the output. Understanding these three lever classes is important for designing and using simple machines effectively in various applications. Mechanical advantage is the ratio of the force applied to the load being moved. It quantifies how much a machine can amplify the input force to produce a greater output force. In a lever system, the mechanical advantage is the ratio of the distance from the fulcrum to the load and the distance from the fulcrum to the applied force. For a pulley system, the mechanical advantage is the number of rope sections supporting the load. More pulleys mean a higher mechanical advantage. On an inclined plane, the mechanical advantage is the ratio of the length of the plane to its height, which helps reduce the force needed to move an object up the plane. Engineering design is a crucial application of moments, as they help ensure the stability, balance, and efficient force transmission in the design of structures, machines, and mechanisms. Architects rely on moments to analyze the stability and load-bearing capacity of buildings, bridges, and other constructions, ensuring the safety and integrity of these structures. In automotive engineering, moments are applied to determine the torque required for steering, braking, and suspension systems, which is essential for vehicle design and performance. Moments are also used in the field of sports and biomechanics to analyze the forces and movements involved in various athletic activities, helping athletes and coaches improve performance and technique. Architectural design is all about carefully calculating moments to ensure the stability and structural integrity of buildings. Moments refer to the forces that act on the different structural elements like beams, columns, and foundations. Architects need to understand the principles of moments to design structures that can withstand gravity, wind, and seismic forces. This allows them to create safe and long-lasting buildings for the people who will occupy them. The image on this slide shows some of the structural calculations and elements that go into this process. Understanding moments is a critical part of the architect's job in creating functional and secure buildings. Engineering relies heavily on the concept of moments to analyze and design structures, machines, and systems. Moments help us understand how forces are distributed and balanced, which is crucial for ensuring structural integrity. Moments are essential in the design of load-bearing components like beams and trusses, allowing engineers to determine the optimal size, shape, and placement of materials. The detailed 3D diagram on this slide illustrates how moments and forces are used in structural engineering analysis. Understanding moments is a fundamental skill for engineers across disciplines, from civil and mechanical to aerospace and beyond. This slide explores the concept of moments and how they are essential in our everyday lives. We'll look at how moments come into play when we're balancing heavy objects, opening jars, and even sitting in a chair. Moments also allow us to magnify the force we can apply using tools like shovels, pliers, and crowbars. Gears, pulleys, and other mechanical devices also rely on moments to help us easily manipulate larger forces, as seen in bikes, watches, and doors. The images on this slide provide visual examples of these moments in action during our daily tasks and activities. The key limitations of moments that we need to be aware of are simplified models. Moments often rely on simplified models that may not fully capture the complexity of real-world systems, limiting their accuracy and applicability. Failure modes. Moments do not always account for failure modes, such as material fatigue or unexpected loading conditions, which can lead to unpredictable outcomes. Computational limitations. Advanced analysis techniques, like finite element analysis, may be required to overcome the limitations of moment-based calculations, especially for complex systems. It's important to understand these limitations when using moment-based analysis and consider more advanced techniques where appropriate. Torque is the rotational equivalent of force, causing an object to rotate about an axis or pivot point. Moments and torque are closely related. The moment of a force is the product of the force and the perpendicular distance to the axis of rotation. Torque causes an object to rotate, while the moment of a force determines the magnitude and direction of that rotational effect. Understanding the relationship between moments and torque is crucial in fields like engineering, physics, and architecture where rotational effects are important. Rotational equilibrium is a state where the net force and net moment acting on an object are both zero. This means the object remains stationary and does not rotate. There are three key conditions for rotational equilibrium. The sum of all forces acting on the object is zero. The sum of all moments or torques acting on the object is zero. The object experiences no rotation. Achieving rotational equilibrium is crucial for maintaining stability in many engineering and physical systems. Understanding these principles helps us design structures, machines, and other systems that can remain in a stable, non-rotating state. Newton's first law states that an object at rest will remain at rest, and an object in motion will remain in motion, unless acted upon by an unbalanced force. This is closely tied to the concept of moments, as moments determine the net force acting on an object. Newton's second law says the acceleration of an object is proportional to the net force acting on it. Moments play a key role in calculating this net force and resulting acceleration. Newton's third law states that for every action, there is an equal and opposite reaction. Moments are essential in understanding how these action-reaction forces balance each other. Moments are fundamental to the study of rotational dynamics, as they determine the angular acceleration and torque experienced by an object. The relationship between moments, work, potential energy, and kinetic energy is a fundamental concept in engineering and physics. Moments are the rotational equivalent of work. The work done by a force is equal to the force multiplied by the displacement in the direction of the force. Moments can influence both potential and kinetic energy. The potential energy of an object depends on its position relative to the axis of rotation, while kinetic energy depends on the object's angular velocity. The principle of conservation of energy applies to moments as well. The total energy of a system, including rotational energy, must be conserved over time. This slide provides a high-level overview of these key concepts, setting the stage for a more detailed discussion of how moments and energy are related. Conservation of angular momentum is a fundamental principle in physics. It states that the angular momentum of a closed system remains constant unless an external torque is applied. This is a key concept for understanding the behavior of rotating objects, from the stability of gyroscopes to the motion of celestial bodies. Rotational inertia is the property of an object to resist changes in its rotational motion. Equilibrium is the state where the net torque on an object is zero, causing its angular momentum to remain constant. The gyroscopic effect is the tendency of a spinning object to maintain its axis of rotation, resisting changes. These principles help explain the stability and predictable motion of many rotating systems in the physical world. Fluid mechanics is the study of how fluids, like liquids and gases, behave under pressure and other forces. Moments are a key concept in fluid mechanics. They describe the rotational effect of a force acting on a fluid. Pressure exerted on a surface can create a moment that causes the fluid to rotate or exert a torque. The buoyant force acting on an object in a fluid can also create a moment that affects the object's stability and whether it floats or sinks. Understanding moments is crucial for predicting and analyzing the behavior of fluids in various applications. Relativity teaches us that moments must be analyzed in rotating reference frames, where the principles of rotational dynamics apply. Moments are crucial for understanding gravitational effects on objects in rotating systems, like orbits and celestial mechanics. General relativity describes gravity as the curvature of space-time, and moments are integral to this geometric interpretation of gravitation. The abstract space-time diagram on the slide conveys these key concepts of relativity and the role of moments in the universe. The core principles of moments, balancing, equilibrium, and rotational dynamics are fundamental concepts that have far-reaching applications across many disciplines. Moments play a critical role in fields like engineering and architecture, as well as in our everyday lives, from structural design to simple mechanical devices. Understanding these principles is essential. As science and technology continue to advance, the study of moments is also evolving, with new discoveries and applications constantly emerging. This is an area of ongoing importance and relevance. This serene, minimalist illustration represents the culmination of learning about moments. The glowing central sphere symbolizes the key principles, while the radiating lines show the wide-ranging applications. Thanks for viewing, and we hope you find the video useful.